Welcome. In this video, we'll be discussing how to test the recovery time of an unknown diode with normal workbench equipment, and that way you can figure out whether the diode may be usable in a switching power supply application or for high frequency signal application. And in this mode of testing, I'll show you it here. A lot simpler lash up than one for testing peak inverse voltage. Let's show you here the simple requirements. Function generator with the cable. I have it wrapped up around here so it won't get in the way of the screen. Going to one of the channels on the oscilloscope, going down to the place where the diode will be under test, hooked to both grounds hooked together, and the other end of the diode under test will be hooked to a load resistor, and then the cable going back up to the second channel on the oscilloscope. Turn the frequency generator, function generator on, turn the oscilloscope on, and set the oscilloscope for XY function or XY display, and set the oscilloscope so that the width is full screen. Oops, wrong setting. So that the width is full screen, and hook up the clip leads directly together, and set the other one so that full height, and you should generate a diagonal display. And then I'll show you what it looks like in a second when I hook a diode up in the place where it should be and sweep it through the frequency here. There's the trace with the leads directly connected where the test diode should go. You see it's a straight diagonal trace. The voltage on a load is exactly the same as the voltage input as it goes up through the scale. Now we'll hook a conventional power rectifier, a 1N4005 silicon diode in the circuit, and you'll see that the line is flat from negative all the way up to 0 volts, and as soon as it passes the junction voltage, then the voltage starts climbing. There's no conduction in that area, and it conducts in that area, and that's around 60 cycles per second. So here's where the fun starts. Well, I'll show you what happens when you start increasing the frequency, and where the recovery time starts playing an effect, becoming part of the equation here. Turn it up to 190-200, still no effect. Turn it up to 900 hertz, 1000, 1600, 2000. You notice something starts occurring here, right? Where the signal is, when the input signal starts dropping back to 0, and it goes into the non-conduction range. A little knee is starting to form here because the diode is still conducting when it drops back to reverse polarity. So turn the frequency back down, go to the 10 kilohertz range, and start turning up the frequency. 3.7, 4, 5, 6, 7, 8, 9. Now it's really obvious at that point. As the voltage swings negative, it reaches a point where it should be going into non-conduction as the current reverses, but since the charge carriers in the diode do not deplete very fast, so to speak, it keeps conducting until the point the charge carriers are depleted, and then it drops back down to 0, which is non-conduction. And you see it's almost a straight solid line, like it's a short circuit, up until the point that it reaches the knee, and then it just drops off. And if you keep increasing the frequency, it'll just keep dragging it out further and further, because, and if you go to around 160 kilohertz, it's almost conducting, staying fully conducting up until the point that the cycle reverses itself and starts heading back up. And so this particular diode is right about 100 kilohertz. This particular diode would be a very poor choice for a 100 kilohertz switching power supply, because when the power supply cycle switches to a non-conducting portion of the cycle, or where the diode should not conduct, it'll stay conducting a good portion of the cycle, which will present a short circuit to the power supply in question. And trying to think of a way to describe this. That's a basic reason for testing the recovery time of a diode, and that's the most evident way to see it with simple workbench equipment. You can sweep it up 14, 20, 25, 26, 30 kilohertz. Let's say leave it at 30 kilohertz, and then remove that diode from test circuit and put in a Germanium diode, high speed, well, RF diode, and you'll see the difference here. Let's put it in wrong, backwards. You'll see at 30 kilohertz, as soon as it drops back down to 0, it is 0 conduction in the negative range, and I can push the frequency all the way up to 140, 150, 200 plus kilohertz, and the line doesn't change much because there is no recovery time to the diode. Of course, you won't use a Germanium diode in a power supply, but that just demonstrates the difference between a diode with a poor recovery time versus a diode with a perfect recovery time. Now, this diode in question is a fast recovery diode. You'll see its rate. As you notice, that knee is still present, but at 200 kilohertz, which is what the frequency generator is currently set at. It's relatively acceptable. Isn't like the germanium diode, but it's definitely not a normal slow recovery AC power supply silicon diode. And next diode under test is a metal case diode. At 200 kilohertz, as you can see, it carries on way to the almost the completion of the negative part of the cycle before it finally stops conducting and then carries back through the rest of the cycle. In this test, we will be doing an old Circus Tarzan 1N1084 ceramic case diode. Well, reverse. Again, carries on down to the point that it's getting close to the completion of the AC cycle. And let's see here, find another one. A little TO220 insulated case double diode. Let's see what it looks like. Well, evidently it's a fast recovery diode, as you can see. There is a little bit of a knee there, but at 200 kilohertz, it's barely noticeable, so its recovery time is pretty fast. Ain't instant, is not instant, but pretty fast. And a little ceramic level case diode. I'll get it right side in. Again, stays conducting almost to the completion of the cycle at 200 kilohertz. And let's see here, a little red package diode with unknown markings. Fast recovery. Just a little knee, and then it goes back to the baseline on the negative side until it hits the junction voltage, goes through the normal positive sweep. And just for reference, a little Schottky signal diode. Not a big Schottky power diode, but a little Schottky small signal diode. Let's see what that thing looks like. As you can see, no knee, because a Schottky hot carrier diode has no recovery time, translation pretty much instantaneous recovery. Takes no time to completely drop the charge carriers when it reaches 0 voltage. So no need present at all, which is the reason why they can be used up into the RF range. And next done in the test, rig 3 amp old salvaged diode from someplace. Again, slow recovery diode, conducts all the way to the point that the cycle is almost completing. If I turn down the frequency, you'll see the knee slowly drop down. But around 100 kilohertz. Yeah, let's turn it down to 100 kilohertz. It's pretty well obvious that that's slow recovery diode. Now I want to show you something here. A large Schottky power rectifier. Hook that in line, and you notice a slightly different display. There's no pronounced knee. It kind of carries a smooth bending line to a point, and then it overshoots as it passes 0 until it hits the conduction point. The reason you see that display is because we have an 800 ohm load resistor, and at 100 kilohertz the capacitance of the diode junction becomes appreciable. So as it passes 0 voltage, the capacitive effect carries the voltage negative. No knee effect again, because the Schottky diode is instantaneous recovery. So it's just the capacitive discharge effect as the load line goes down to its negative peak. And once it reaches a negative peak, the capacitive effect carries the voltage back positive before it reaches the actual 0 point, causes the overshoot till it reaches the positive bias across the junction and carries to its positive peak. And on large power rectifiers, you'll see high-speed ones like Schottky ones, you'll see that shape of a display, but as I said, it does not indicate that it's a slow recovery diode. It indicates that it's a huge junction with a lot of capacitance, because if it was recovery time causing the display, it'd be a straight conduction line out until you hit a specific point where the charge carriers deplete, and then it would take an abrupt turn back to 0, and that's what generates that knee. Now to the next diode. Again, a traditional plastic case silicon 1 amp diode. That one's a real poor recovery. Even at 100 kilohertz, it's pretty much reaching peak negative voltage before it turns loose, stops conducting, and you see that sharp knee there, drops back to 0 and returns. Then we get to let's see here, find it here. Stuff running around the workbench, can't find it. In here, where'd it go? A big stud mount diode. put that in the circuit. Yeah, again, pole recovery. It's not the sharp, not quite a sharp knee. If we turn the frequency down a bit where the capacitance of the diode junction stops playing an effect, down to 11 kilohertz, you can see the sharp knee form till it returns back to its normal path. Now let's take another one, the painted diode that someone spray painted that I showed in the first video. Let's see what its recovery time is. Again, this is still at 11 kilohertz. The very sharp knee where it conducts all the way out to the point that it's reaching a considerable portion of the negative cycle before it finally turns loose. And next one, whoops, bump. Oh well. Next one is a slightly unknown small little case diode. Don't even know which end is cathode or anode. Well, that one at 11 kilohertz, so let's crank up the frequency. Well, about 100 kilohertz. You can see the waveform pretty sharp, so it's a standard slow recovery diode. Alright. Let's see here. That pretty much concludes this video on how to test recovery time of a diode using a function generator and an oscilloscope. Next video we'll be measuring the forward voltage drop of a diode under low and high current conditions, and using that information to try to determine what technology a diode it may be: Germanium, Schottky diode, or a silicon diode. And we'll also be talking about how to roughly estimate the forward current carrying capability of diodes in question. So, see you there. Take care.